When you ask an AI to write, a heartfelt poem or debug a complex block of computer code, it doesn't actually know the poem is.
No, not at all.
It doesn't know what code is. Honestly, it doesn't even know what words are.
Yeah, and that is a jarring realization. I mean, we are hardwired to project human understanding onto anything that, well, mimics human communication.
Right, totally.
So when a machine produces something that feels creative or insightful, our brains immediately struggle to categorize it as anything other than conscious.
Exactly. There is a very famous quote by the futurist Arthur C. Clarke. Any sufficiently advanced technology is indistinguishable from magic.
Oh, absolutely.
And watching these large language models instantly synthesize a massive report in like 3 seconds, it really does feel like someone waved a wand. It feels like wizardry.
It really does.
But for this deep dive, our mission is to pull back the curtain on that exact magic trick. We are taking you, the listener, from feeling like you're interacting with some mystical oracle to truly understanding the mechanics underneath generative AI and AI agents.
Because, spoiler alert, there is no wizardry in the box.
Right.
What looks like magic is really just the rigorous application of mathematical techniques. It's statistics, data science, and probability running at a scale that is, frankly, difficult for the human mind to easily comprehend.
Yeah, it's massive.
But once you demystify the system, you stop being a passive consumer of a black box. You start seeing the levers you can actually pull to make this technology work for you.
Okay, let's unpack this, because going from, magical robot friend to layers of refined math is a huge mental shift.
It is a big leap.
I want to translate that math back into plain English so we can finally grasp how the trick is done. So, let's start at the very beginning. How does a large language model, an LLM, actually read our language?
Well,
Because it's not reading like you and I do.
yeah.
Fundamentally, these models are trained to do one basic thing, right? Generate completions based on prompts. They are basically super powerful versions of the predictive text on your cell phone.
That's a great way to look at it. Consider a simple sentence. I heard a dog bark loudly at a cat.
Yeah.
Imagine you only heard the first part. I heard a dog.
I mean, I instantly expect the next word to be bark.
Exactly. But why is that? It's because you possess a massive vocabulary, you understand common linguistic structures, and crucially, you understand semantics.
Right, the meaning.
You know that if you heard something, it has to be a sound. You know what specific sound the dog makes.
Yeah.
You are narrowing down probabilities based on a lifetime of living in the real world. The monumental challenge for researchers was figuring out how to train a mathematical model confined to a silicon chip to have those exact same predictive abilities.
And the answer to that starts with a process called tokenization, which is wild, by the way, because it completely changes how you look at the text on your screen.
It really does.
The AI doesn't see sentences, and it doesn't even see individual letters. It breaks language down into chunks called tokens. To me, it's like dismantling a giant Lego castle.
Oh, I like that.
Instead of seeing the whole castle, the sentence, the AI breaks it down into individual numbered Lego bricks to process it.
Wait, so it doesn't actually read English, it just reads a massive sequence of numbers.
Yes. What's fascinating here is that this mathematical translation is the absolute bedrock of all AI functionality. A machine cannot process the letter A.
Right.
It can only process numbers. So tokenization takes a sentence and assigns an integer ID to every single chunk of text. In a highly simplified example, the word I becomes token number 1, heard becomes token 2, A is 3, dog is 4.
But tokens aren't always whole words, right? I think of it almost like a massive box of those magnetic poetry tiles you put on a fridge.
Yes, perfect analogy.
Some of the tiles are full words, like dog or apple. But some of the tiles are just, well, pieces of words.
That's a very helpful way to visualize it. Tokens include whole words, but they also heavily rely on subwords. Take the word unbelievable.
Okay.
The AI might not have one single token for unbelievable. Instead, it breaks it down into chunks it sees often. The prefix un gets its own unique numbered token. Oh, wow.
The core believe gets a token. The suffix able gets a token. Even punctuation marks and, blank spaces have their own specific integer IDs.
So it's hyper efficient. It doesn't need to learn every single variation of a word if it just knows the building blocks.
Precisely. As modern models train on terabytes of data from the internet, they build an immense dictionary of these tiles.
That's huge.
The latest generation of large language models have vocabularies consisting of hundreds of thousands of these unique numbered tokens.
Okay, so I type, I heard a dog, and the machine literally just sees a sequence of numbers, like 1, 2, 3, 4.
Exactly.
But wait, If the AI only sees a raw sequence of integers, how does it know what those numbers actually mean?
That is the million-dollar question.
How does it know that token 4 dog is related to a puppy, but has absolutely nothing to do with a skateboard? I mean, a number 4 is just a 4.
Right. And this brings us to the core architecture that makes modern AI possible, the transformer model, and specifically the concepts of vectors and embeddings.
Vectors and embedding.
This is where those simple, flat integer IDs get a massive upgrade. The system assigns every single token a vector.
A vector. Okay, my high school math is a little rusty. What does a vector look like in this context?
A vector is simply an array of multiple numeric values. Instead of dog just being the number 4, dog is represented by a long list of numbers.
Like coordinates.
Yes. In a grossly simplified example, it might be the array 2, 7, 11. In reality, a modern LLM uses vectors that have thousands of dimensions, thousands of numbers, just to represent one token.
Okay, here's where it gets really interesting, because those thousands of numbers aren't just random, they act as coordinates.
Exactly.
Imagine a massive, sprawling, multidimensional map of human meaning. If you take the coordinate numbers for the concept of dog and drop a pin on that map, and then you drop a pin at the coordinates for puppy, they are right next door to each other.
That's right.
Their vectors point in almost the exact same direction.
To visualize this, let's compress those thousands of dimensions down to a 3D spatial map, like looking at stars in a galaxy.
Okay, I'm with you.
The vector for dog might place it at coordinates 10, 3, 2. The vector for puppy places it at 5, 3, 2. They share very similar semantic space.
Because they mean similar things.
Yes. Cat is somewhere close by in that same solar system, maybe at 10, 3, 1. But skateboard. Skateboard is pointing off into a completely different galaxy with coordinates like -3, -2, 2.
So the AI is literally navigating a geographical map of human concepts. But how does it measure the distance between those stars?
Through a mathematical calculation called cosine similarity.
Cosine similarity. Okay, break that down for me.
Imagine standing at the center of our 3D galaxy. You draw a straight line from yourself out to the star labeled dog.
Yep.
Then you draw a second straight line to the star labeled puppy. Okay. Cosine similarity simply measures the angle between those two lines.
Oh, like using a protractor.
Exactly like that. If the angle between the lines is very small, nearly 0 degrees, the lines are pointing in the same direction.
Making them similar.
Right. The cosine similarity is very high, telling the math that these two concepts mean almost the same thing. If the angle is wide, say 90 degrees, or pointing in totally opposite directions, the cosine similarity is low, meaning the concepts are unrelated.
That is brilliant, but it begs a massive question. Who drew the map? I mean, how does the AI figure out those coordinates in the first place to know that dog and puppy belong together?
The AI builds the map itself during its initial training phase, using that transformer architecture we mentioned.
Ah, okay.
A transformer has two main halves, an encoder and a decoder. The encoder's job is to read the input text and understand the context. It uses a mechanism called attention to do this.
Attention, meaning it pays attention to the surrounding words.
Yes, exactly. It examines each token one by one and looks at the tokens surrounding it to see how they influence each other.
Okay.
If it processes the word bark, it pays a lot of attention to the words herd and dog earlier in exactly the same sentence. It mathematically assigns them higher weights because they heavily influence the context of the word bark.
But sentences are complicated. I mean, bark could be the sound a dog makes, or it could be the outside of a tree.
Which is why the architecture uses multi-head attention. If we connect this to the bigger picture, multi-head attention is like having a panel of different experts evaluating a sentence simultaneously.
Oh, I see.
One head might purely analyze the grammatical structure, finding the subject and the verb. Another head might look at historical context. Another head looks for emotional tone.
So they're all working at once.
They are all evaluating the token in parallel. By processing billions of sentences during training, the model constantly adjusts the vector coordinates based on how frequently these tokens appear together and in what contexts.
So it learns entirely through brute force statistics that dog and bark are deeply related, while tree and bark have a completely different mathematical relationship depending on the surrounding words.
That's the encoder building the context.
Yeah.
Then the second half of the transformer, the decoder, takes over.
The decode.
The decoder uses this incredibly rich, multi-dimensional map of embeddings to actually generate the output, predicting the next word.
Wait, does the decoder use that same multi-head attention?
It does, but with a twist. It uses masked attention.
Masked.
Yes. When the decoder is trying to generate the next word, It is mathematically masked or blinded from seeing any words that come after its current position.
Because they haven't been written yet.
Exactly. It can only look at the tokens that have come before it. If the sequence it has generated so far is when my dog was a woo, it evaluates those previous tokens, navigates the embedding space we talked about, calculates the cosine similarity, and determines that the token for puppy has the highest mathematical probability of coming next.
Wow. Okay, so the magic trick is fully revealed. There is no little ghost in the machine that understands poetry.
Not at all.
It's a massive multidimensional probability calculator. But, this realization actually creates a practical challenge for you, the listener.
How so?
If the AI is just navigating this vast mathematical map, how do you steer it? How do you force it to go to the exact location you need for your specific task?
That is the art and science of prompts. A prompt is the input you provide to trigger the generation.
Right.
But it's not as simple as just typing a question. There are distinct layers to prompting, primarily system prompts and user prompts.
The system prompt is fascinating because most everyday users never even see it. It's like the hidden set of instructions that dictates the AI's entire persona and behavior before you even type hello. It sets the absolute guardrail.
Yes, exactly. When you open a commercial AI chat application, the developers have already fed it a system prompt.
Like what?
It might say, "You are a helpful corporate assistant. You respond concisely. You never use profanity, and you must decline to answer medical questions." It establishes the boundaries of the probability space.
And then the user prompt is my actual request, like summarize this marketing email in 6 bullet points. The AI takes my user prompt and generates the text, but it's doing so while locked inside the cage built by the system prompt.
And to maintain the illusion of a continuous conversation, the application acts as a middleman. It maintains a conversation history.
So it remembers.
Well, not exactly.
Yeah.
Every time you send a new user prompt, the application secretly bundles your new question with a summary of everything you've discussed in the last 10 minutes and sends that entire package back to the LLM.
Oh, wow.
That's how the model seems to remember what you were just talking about.
Okay.
It doesn't actually have a memory. It's just being refed the context every single time.
Okay, but I'm going to play devil's advocate for a second.
Go for it.
If the AI is this incredibly sophisticated, multi-dimensional, attention-calculating genius, why does everyone say the key to a good prompt is to talk to it like a toddler?
Give me an example of what you mean by that.
Well, the standard advice for prompting is always be explicitly clear. Add extreme context, use examples, ask for a specific structure. If it's so smart, shouldn't it just intuit what I want? It feels like managing a brilliant intern who has zero real-world common sense.
That's a funny way to put it.
You have to say, I want a summary, I want it in a bulleted list, I want an optimistic tone, and do not make it longer than 1 page. If you don't do that, they hand you a 500-page novel.
This raises an important question, and it's exactly why we need to strip away the illusion of AI intelligence. We constantly project human intuition onto the model.
Right.
But remember the mechanics. The AI doesn't understand your business needs. Vague language like "give me a summary" results in a vast, sprawling probability space. The map could point in 1,000 valid directions.
So it's not being difficult, it's just mathematically lost in the galaxy.
Yes, explicit instructions, providing a persona, defining the format, and giving examples of the desired output. All of those toddler-level instructions dramatically narrow the multidimensional space.
I see.
You are using words to place heavy mathematical weights on specific vectors, forcing the cosine similarity to point directly at the precise outcome you need.
The more guardrails you put up, the tighter the prediction. That makes total sense. But we hit another wall here. An LLM's map of meaning is generic, right?
Usually, yes.
It was trained on the public internet up to a certain date. What happens when you need it to be specific to your private data?
That's a huge issue for businesses.
For instance, what if I open a generic LLM and ask, what is the maximum I can claim for travel expenses on my next business trip?
A generic model will either hallucinate a plausible-sounding number, give you a generic IRS guideline, or politely tell you to consult your HR department.
Right.
It has absolutely no vector coordinates for your specific company's private policy.
Exactly. And that is where an architecture called RAG comes in, Retrieval Augmented Generation. I want to spend a minute here because RAG sounds incredibly intimidating, but the mechanics of how it solves this problem are brilliant.
It is the definitive solution for grounding an AI's mathematical predictions in your specific private reality.
Let's break down the mechanics of RAG step by step. Let's say I'm using a custom AI tool built for my company, and I type in my user prompt. What's the max travel expense I can claim? How does RAG handle that differently than a normal ChatGPT window?
In a RAG setup, the application intercepts your prompt before it ever reaches the LLM.
Okay.
Step 1 is retrieval. The app takes your question and converts it into a mathematical vector. It then searches through a private knowledge base, say, a secure database containing all your company's HR PDFs and policy documents.
Using that cosine similarity we talked about,
Exactly.
it's looking for documents that have a mathematical proximity to travel and expenses.
Yes. It scans the database and retrieves the specific paragraphs from the 2024 Employee Handbook regarding travel limits.
Got it.
Step 2 is augmentation. Behind the scenes, totally out of your view, the application takes your original prompt and augments it. It effectively pastes the text of the Employee Handbook right next to your question, creating a massive, highly detailed mega prompt.
It's sneaking an open book test into the prompt.
That's a perfect analogy. Finally, step 3 is generation. It sends that massive augmented package to the LLM.
And then the AI reads it.
Well, the AI's multi-head attention mechanism now evaluates your question while heavily weighing the context of the handbook text sitting right there in the prompt. It navigates the probabilities and generates a completion like, according to your company policy, you can claim up to $150 per night for a hotel.
It perfectly bridges the gap between general mathematical probability and practical utility for my specific life.
It really does.
It didn't need to be trained on my company data. It just needed the data temporarily injected into its immediate attention span.
Which brings us to a massive paradigm shift. Up to this exact moment in our discussion, we have been treating the AI as a purely passive entity.
Yeah.
You ask a question, it retrieves data, it generates text on a screen, but it just sits there.
Right. It's a very smart talker. It can tell me my budget is $150, but it can't actually book the hotel for me. What if you need the AI to take action?
That requires stepping beyond large language models and entering the domain of AI agents.
Agents.
An agent is a system that doesn't just answer questions, it executes workflows. It transitions generative AI from passive text generation to active, real-world task automation.
So what does this all mean? How do we mechanically turn a probability calculator into an active doer?
An AI agent requires 3 distinct components to function. First, it needs a brain.
The LLM.
Right, the brain is the LLM we've been discussing. It provides the natural language understanding, the reasoning, and the ability to process prompts. Second, it needs instructions.
Like a system prompt.
Exactly, a robust system prompt defining the agent's exact role, its limitations, and its workflow logic. And third, the critical missing piece. It needs tools.
Tools. This is where the magic really starts to feel real again. Because an LLM trapped in a server can't interact with the world. But if you wrap it in an application that gives it tools, everything changes.
Broadly, there are knowledge tools and action tools. A knowledge tool is giving the agent API access to external systems it wasn't trained on.
Like what?
It could be live access to the Bing search engine, or a direct pipeline into your company's live Jira ticketing system.
And action tools are the hands.
Yes. An action tool allows the agent to execute commands. When you ask the agent to email the client the updated budget, the LLM's brain generates a specific string of text, like a block of code, that the surrounding application recognizes as a trigger.
Okay.
The application then uses an action tool to interface with Microsoft Outlook and actually hit send on that email. It can update a calendar, push code to a repository, or even control a physical smart home device.
So by combining the LLM brain with these tools, I'm not just typing into a calculator anymore. I am deploying a mini robotic workforce right from my laptop.
You are. And the frontier of this technology where the industry is moving right now is multi-agent systems.
Multi-agent.
Instead of trying to build one monolithic, godlike AI that can do every single part of a complex business workflow, developers are building specialized teams of agents that collaborate.
A digital assembly line. How does a team of mathematical models actually work together?
It looks remarkably like a human team. Imagine a workflow for creating a weekly competitive analysis report. You might have one agent, the researcher, whose only job, defined by its instructions, is to use knowledge tools to scrape the web for news about your competitors.
Okay, so the researcher gathers the raw data.
Then the researcher passes that raw data to an analyst agent. The analyst doesn't have web access.
Oh, it doesn't.
No, its instructions are strictly to use its LLM brain to reason over the text, find patterns, and calculate cosine similarities to identify threats. Once the analyst forms conclusions, it passes the baton to an execution agent.
And that one has the hands.
Right. The execution agent uses action tools to format a polished email and send it to your executive team.
But wait, how do they pass the baton? How do they communicate with each other?
Through prompts.
You're kidding.
Not at all. They use natural language generation to prompt each other. The researcher agent generates a prompt containing its findings and sends it as an input to the analyst agent.
That is wild.
The analyst generates a prompt and sends it to the execution agent. They evaluate tasks, assign responsibilities, and even critique each other's outputs entirely through the automated exchange of text prompts.
Okay, let's take a breath and recap the incredible journey we've just been on. We started with Arthur C. Clarke's observation that advanced tech looks like magic. And it does.
It definitely does.
But we pulled back the curtain. We saw that the AI isn't reading English, it's breaking language down into tokenized puzzle pieces. It takes those pieces and maps them across a massive multidimensional vector space, using transformer models and multi-head attention to calculate the mathematical proximity of human concepts.
And we learned that we aren't just helplessly floating in that space, we can steer the machine.
Right.
It can narrow the probability space using precise user prompts and hidden system prompts. And we can ground the model in our own private reality, using the retrieval and augmentation steps of RAG.
And finally, we handed that mathematical brain a set of API tools, transforming it from a passive text generator into an active AI agent capable of collaborating in multi-agent systems to execute real-world tasks.
Yes.
For you, the listener, the takeaway here is deeply empowering. You are no longer just a passive consumer staring at a magical black box.
Yeah.
You now understand the gears, the tokens, and the math underneath the illusion. That makes you incredibly equipped to actually wield this technology effectively in your own life and work.
It is empowering. But before we wrap up, I want to leave you with one final, slightly provocative thought to mull over.
Okay, let's hear it.
We just talked about multi-agent systems where specialized AIs collaborate to execute workflows by sending natural language prompts to one another. But think about the underlying mechanics we've uncovered.
The tokens and vectors.
Right. English is a slow, clunky, ambiguous language designed for biological human vocal cords. If these agents are ultimately just calculating vectors and tokenized math, what happens when human language is no longer the most efficient way for them to communicate with each other?
Oh, wow.
As multi-agent systems evolve, will these AIs eventually bypass English altogether? Will they invent their own hyper-efficient mathematical shorthand to pass data back and forth? A language born entirely of multidimensional statistics that we humans can no longer read or decipher.
Wow. From layers of math right back to magic. That is something to think about. Thank you for joining us on this deep dive into the mechanics of generative AI. Stay insanely curious, keep experimenting, and we will see you on the next deep dive.